All right, we're going to start with a warm-up that you want to be able to do without a calculator. We're going to make sure we all have the same base knowledge of exponents and how they work. You're going to evaluate each exponential expression. Evaluate means to find the value of. So find the value of 2 to the third, find the value of 5 squared, 3 to the negative 2, and 8 to the 0th power. Next, let's find those answers here. 2 to the third power means 2 times 2 times 2, and 2 times 2 is 4, 4 times 2 is 8, and so this whole thing is equal to 8. 5 squared means 5 times 5, which is 25. 3 to the negative 2 power, you should remember that negative exponents mean we are going to divide instead of multiplying. So we're going to divide 1 divided by 3 squared. That's what 3 to the negative 2 power means. And 3 squared means 3 times 3. So this is 1 divided by 3 times 3. And 3 times 3 is 9, so this is 1/9. So negative exponents mean we divide instead of multiplying. So instead of multiplying by 9, we're dividing by 9. And we're supposed to remember that anything to the 0 power is 1. Okay. The next two problems are kind of a preview of what we're going to be looking at in a little while. And so without a calculator, just give yourself a minute to think about this. What exponent needs to be put on 2 to get to 16? We're asking 2 to what power gets us 16? And the answer is 4. And the reason the answer is 4 is because 2 to the 4th equals 2 times 2 times 2 times 2. 2 times 2 is 4, 2 times 2 is 4, and 4 times 4 is 16. So we need 2 to the 4th power. For what value of x does 3 to the x give us 27? We're looking for what number needs to go here to get to 27, and the answer is 3. 3 to the 3rd power means 3 times 3 times 3. 3 times 3 is 9, 9 times 3 is 27. And so 3 to the 3rd power gives us 27, the answer is 3. Today, we're going to be learning about a new type of inverse function. We're going to be learning about logarithms, and we will go much more into depth in them later this year. Logarithms is a very long word, and so we say logs for short. And logs, or logarithms, are the inverse of exponential functions. Exponential functions are quite important, and learning the inverse of them enables us to do a lot of things with exponential functions we wouldn't be able to do otherwise. So that's why we're going to be learning about logarithms. This is how we write a logarithm. You will notice that it says log, okay, like you might expect. And then this b is lower down, and the a is higher than the b. But you might notice that the a is the same height as log. A is not an exponent here. In fact, the only thing that's off the normal line is this b, and it's lower down. And the way we read this is log base b of a. Sometimes we will put a in parentheses, just like we say f of x. This is log base b of a. And it asks the question, what exponent needs to go on b to get you a? Or another way to think about that is, if b to the x equals a, find x. Find the exponent you need to put on b to get to a. A lot of times I imagine a little blank empty box right here for where the exponent needs to be. It's like b to what power could get me to this a. Okay, so today on this, you're watching a video on this. In class, we would be spending a lot of time talking, and kids would be practicing speaking this. So you're going to need to do your best to say this in your head a bunch of times. It's very easy to say this wrong if you're not practicing it. And so I want you to be using the language in your head. When you read this, read to yourself. Every time you see a logarithm, read to yourself what it says so you can get on the right track of saying it the right way and not get in a bad habit. This says log base 2 of 8. Log base 2 of 8. And log base 2 of 8 asks the question, and again, we could put parentheses here if we wanted to, log base 2 of 8 asks the question, what exponent goes on 2 to get to 8? 2 to what power gets us 8? And so we can write the answer to this as, we can evaluate a logarithm. Log base 2 of 8 is equal to 3. So this log has a value of 3. 3 is the exponent that we needed to put on 2 to get to 8. Hopefully we can see the relationship between logs and exponents. Okay, so as you're doing these, I want you to evaluate, which means find the value of, and say it to yourself out loud. So, for instance, on this first one, when you're reading it, and for each other one, say to yourself, log base 3 of 9. I would actually prefer if you said it out loud, even if you're sitting in a room by yourself somewhere. It will help your learning. Log base 3 of 9 is equal to what? So you're going to evaluate all of these and say them out loud. Log base 3 of 9 equals 2, because 3 squared is 9. Log base 10 of 100,000 is 5, because 10 to the 5th power gives you 100,000. If you don't know this multiplying by 10s trick, every time you multiply by numbers that end in zeros, you can just multiply the front numbers together. 1 times 1 times 1 times 1 times 1 is 1. And then 0, 0, 0, 0, 0. You can just count up the numbers of zeros, and that's the correct number. So 1, 2, 3, 4, 5 zeros gives us 5 zeros. So we need 5 tens to multiply together. Log base 5 of 125. Again, make sure you're saying it out loud. Log base 5 of 125 is 3. And that's because 5 to the 3rd power equals 125. 5 times 5 is 25, times 5 is 125. All right, let's do a little bit more work on special exponents. We saw this a little bit in our warm-up, but let's make sure we feel good about it. When we have a negative exponent, 4 to the negative 2 power means negative exponents tell us we will divide instead of multiply. So 1 divided by 4 times 4. So instead of multiplying 4 times 4, we divide 1 divided by 4 squared. And so this is 1/16. Anything to the 0th power is 1, and anything to the 1 power is itself. So these are some exponents we should know from Algebra 1, and we're going to use them in our evaluating logarithms. So as you're evaluating these, again, say to yourself in your head what the log is asking, and then think about what the answer is. We'll go over it. Log base 73 of 1, make sure you're saying it out loud, is asking 73 to what power will give us 1. And we just talked about up here how anything to the 0 power is 1, and so the answer to this logarithm is 0. Here, we see that there's some dividing. And so we know that 4 is going to be to some negative exponent. And the question is what? Well, 4 to a negative exponent gives us 1 divided by. And so 4 to the negative 3 will be 1 divided by 4 times 4 times 4. 4 times 4 is 16. 16 times 4 is 64. And so the answer is the exponent needs to be negative 3. And you can tell it's going to be negative if it's got a 1 divided by it, because that's what a negative exponent will do. The last thing is log base 57 of 57, and it's asking you what exponent goes on 57 to get to 57, and the answer is 1. 57 to the 1 power equals 57. All this stuff down here is just work I am showing. It's not the answer. None of this has anything to do with it has something to do with the answer, but the answer to the logarithm is just the value of the logarithm. 0, negative 3, and 1. Okay, try 3 more. Here, 2 to what power gets us 1/8, and we can tell it's a negative number. I know the answer will be negative because 2 to a negative power will be 1 divided by. And so how many 2's do I need to multiply together to get to 8? Well, I need 2 times 2 is 4, times 2 is 8. So I need 3 2's multiplying together, and so the answer to this logarithm is negative 3. 2 to the negative 3 power gives us 1/8. Because 2 to the negative 3rd is 1 divided by 2 times 2 times 2. Log base 3 of 1/9 is asking us 3 to what power gets us 1/9. And so we know 3 will need to be a negative exponent, because we need the 1 divided by. That's what the negative exponent does. So 1 divided by 3 squared, and so we need a negative 2 exponent. So 3 squared is 9, and so that's how we get to 1/9. 3 to the negative 2 power gets us 1/9. And the last one, 4 to what power gets us 1? And the answer is 0 because anything to the 0 power is 1. All right, we're going to use this skill to to find the inverse of an actual exponential function. So here we have f of x equals 2x, and this same process would work for any exponential. We're going to start by making a table. And I'm going to start with 1 because I think that's the easiest thing. So f of 1, 2 to the, when x is 1, 2 to the 1 power is 2. When x is 2, 2 squared is 4. And when x is 3, 2 to the 3rd power, I sometimes see people do 3 squared here. 2 to the 3rd power is 8. And now we've got some special exponents. When x is 0, 2 to the 0 power, anything to the 0 power is 1. When x is negative 1, a negative power means 1 divided by 2 to the 1st. So 1 divided by 2. So 1/2. When x is negative 2, 2 to the negative 2 power means 1 divided by 2 squared. That's what a negative exponent tells us. It tells us 1 divided by. So 1/4. And when x is negative 3, 2 to the negative 3rd power means 1 divided by 2 to the 3rd power, and that is 1/8. One thing we should notice is that this has a constant multiplier of 2. We can see it's multiplying by 2 here, multiplying by 2 here, multiplying by 2 here. If we go back the other direction, it's dividing by 2, dividing by 2, dividing by 2. 1 divided by 2 is a half. If you take a half and divide it into 2 parts, you get a fourth. And so these are also all multiplying by 2 as we go up. So this is a constant multiplier as we would expect with an exponential. We should already know what an exponential parent function looks like. Exponential parent functions have a point at 0, 1, as we have here. Here's our point at 0, 1. And they grow, they grow exponentially, meaning that as you go to the left, they go towards an asymptote. And as you go towards the right, they grow faster and faster and faster. And we can see these points here. Here's this point 1, 2. Here's this point 2, 4. Here we've got the point when x is negative 1, y is 1/2. We have all the points we would expect. All right, let's do the inverse function. Let's look at f inverse of x. And so finding the inverse of a table is something we should know how to do. We can find the inverse of this table by switching the x and the y. And so I'm just going to go ahead and take each x and switch it. So instead of y being 1/8, x is 1/8. And when x is 1/8, y will need to be negative 3. This is 1. When x is 1/4, y will be negative 2. I just took these and switched x and y. It's how we find the inverse of a table. When x is 1/2, y will be negative 1. When x is 1, y will be 0. When x is 2, y will be 1. When x is 3, when x is 4, y will be 2. And when x is 8, y will be 3. And this came, you can see that each of these x and y points, 3, 8, got switched into 8, 3. Okay? We can put these on a graph, and I'm going to go ahead and do it in red here. And we also could have just taken the points on this graph and switched the x and the y. For instance, 2, 4 would become 4, 2. I apologize. 4, 2. And that's coming from switching the x and the y. But I'm just going to graph these points in the table because I've already made a table of it. When x is 1/8, y is negative 3. When x is 1/4, y is negative 2. When x is 1/2, y is negative 1. And when x is 1, y is 0. When x is 2, y is 1. We already put 4, 2 here, and then we've got when x is 1, 6, 7, 8, y is 3. So here is our graph. Of course, we should know that the relationship between these two graphs is that they are reflected over the line y equals x. And we can see that here, that these are a reflection across y equals x. And so the question is, what is the equation that makes this graph? And so we're going to find the inverse of this equation. We also know how to find inverses of equations. We take the y value, that becomes x. We take the x value, and that becomes y. And it turns out that the inverse function of an exponential is a log. And so what we do, I'm going to rewrite this here, is we're going to do log base 2 on both sides. Log base 2 of x equals log base 2. I'm doing log base 2 of both sides. And we will learn more about this later this year. You don't need to feel like you're an expert in this inverse operation yet. If you're a little confused, it's okay. I'm doing the same operation on both sides. Log base 2 of x cannot be simplified, but this is saying 2 to what power gets me 2 to the x? And hopefully we can see that the answer is x, that 2 to the x gives us 2 to the x. And so the answer to this logarithm is x. So we get log base 2 of x. Oh wait, oh my goodness guys, this was a y. I apologize. Log base 2 of 2 to the y will be y. I'm so sorry if that was confusing. This was 2 to the y. We did log base 2 of 2 to the y. And so it's saying 2 to what power? That's what the log is asking. It's saying 2 to what power gets us 2 to the y? And the answer is y. So our answer is y equals log base 2 of x. And so we're going to rewrite that as f inverse of x. So f inverse of x equals log base 2 of x. And we can see that that's correct for all of these points. For instance, if I take 8, f inverse of 8 means log base 2 of 8. 2 to what power gets us 8? And we can see the answer was 3. So this is our graph of y equals log base 2 of x. And this is kind of our last parent function we're going to have for a while. It is logarithm functions. We're going to just write the logarithm parent functions. So log functions all have a lot of similarities because they're all the inverse of exponential. All log functions will have a point at 1, 0. And this is because they're the inverse of exponential. Remember that exponential parent functions all have a point at 0, 1. So log parent functions will have a point at 1, 0. All exponential functions had an asymptote at y equals 0. And so all log functions will have an asymptote at x equals 0. And all log functions will be increasing but concave down. So this function is increasing, but it is bending down. So increasing, but concave down. So even though the function is going up, it is bending downwards, and that means it's growing more and more and more slowly. For instance, in this function log base 2 of x, to go from y equals 0 to y equals 1, you only had to have x go over by 1. But then to go from y equals 1 to y equals 2, you had to go over by 2 spaces. To go from y equals 2 to y equals 3, you had to go over by 4 spaces. X had to increase by 4. To go up from y equals 9 to y equals 10, x has to go over by like 512 spaces. So the higher up you go, the further x has to increase. But this won't have, there's no horizontal asymptote. Even though it looks like it might be bending down, it doesn't come back down like a parabola, and there is no horizontal asymptote. The domain, we can see the x values it is defined for. There are no x values over here. The domain is x is greater than 0, or in interval notation, we know to write it as 0, infinity with a parentheses on the 0 because there is no x at 0. In other words, log for this was log base 2. Log base 2 of 0 is undefined, as is any log of a negative number. That's also undefined. There won't be any values. Kind of similar to square roots in that regard. The range of log functions, well, I see that the y values continue to go down, and I see this arrow at the end, the y values will continue to go up. So the range is all real numbers, or we could say negative infinity is less than x is less than infinity, or we could say negative infinity, comma, infinity. Ooh, a mistake. This should say negative infinity is less than y is less than infinity, because this is the range, it's the possible y values we're describing. So that's all you need to know for log parent functions. We will learn a lot more about them later this year.